38. CPS geometry. Discrete complex planes. The complex plane is defined as a modified Cartesian plane. The x-axis is used to represent the real part of complex numbers, and the y-axis is used to represent the imaginary part of complex numbers. The Gaussian integers are complex numbers, whose real part and imaginary part are both integers. The Gaussian integers are represented as points on the discrete complex plane. For this plane, the real axis and the imaginary axis have units of length equal with 1. This discrete complex plane was popularized by Gauss, with his study of complex prime numbers, known as Gaussian primes. These complex numbers are the equivalent of regular prime numbers. Let's extend the notion of discrete complex plane to the full spectrum of CPS planes. As seen in the previous videos, there are an infinite number of CPS plane patterns, generated by the close packing of spheres arrangement. The natural way of defining these planes is based on the use of the CPS version of the Brahmagyupa's identities. The units of length for the real axis and the imaginary axis are given by the square root of two square free numbers, p and q. The coordinates of a point belonging to this plane, in combination with the units of length of the axes, provide a way of connecting the CPS points to the terms, or the factors, in the Brahmagyupa's identities. Let us look closer to the multiplication from a pure geometrical point of view first. The algebraic form of the discrete complex numbers we will end up with shall be able to cover all the geometrical points connected by multiplication. For the geometrical representation of these points, a multiplication factor is needed. This factor is required if we want the coordinates of the product to be commensurable with the two factors of the multiplication. As already observed, the multiplication of two numbers belonging to this plane can generate two numbers belonging to the same plane. The magnitudes of these two numbers are equal. Their arguments, or their orientation, are given by the sum, respectively by the difference, of the arguments of the initial two numbers. These numbers belong to the CPS lines associated with these CPS points. The symmetry, apparently hidden in the distribution of the CPS lines, is contained, and is now revealed, by the process of multiplication. By playing with the signs of the coordinates of the two numbers, one can generate 3 more sets of two numbers. In this example, each set belonged to different quadrants. All 4 sets can be thought as being generated by the same two numbers. All the resulting numbers have the magnitudes equal with the product of the magnitudes of the two initial numbers. The orientations of these lines, corresponding to each quadrant, are symmetrical relative to the real axis and the imaginary axis. Once the orientations of two lines are known, the orientations of all the others can be found easily by reflecting the initial lines relative to the two axes. We also can imagine 3 more sets of initial lines, 1 set in each quadrant. The magnitudes of the lines in each set are equal among themselves. The orientations are again obtained by simple symmetry. In this case, each quadrant can be treated independently. For this example, the products of two numbers belonging to any given quadrant are two numbers, also belonging to the same quadrant. It is time to get to the final conclusion regarding these multiplications. After some careful considerations, one has to recognize that to get all these symmetries, 2 variants of the initial complex numbers are needed. Let's consider a complex number, A equal with x multiply by the square root of p plus I multiply by y multiply by the square root of q. X and y are the coordinates of the complex number A. The square root of p and the square root of q are the units of length for the real axis and the imaginary axis. I is of course the square root of -1. By changing the signs of the real part and the imaginary part of the initial complex number A, one can generate three more complex numbers, B, C, and D. The complex conjugate number, B, is the best known among these new complex numbers. But all these four complex numbers, A, B, C, and D, are needed if we want to completely associate complex numbers with all the CPS points belonging to a CPS plane. At this point in our investigation, it have to be clear for everyone that the complex multiplication, as defined and used in complex analysis, can generate all the possible orientations of similar CPS lines. Don't forget, in the most general case, when the units of length, for both axes, are equal with incommensurable square root numbers, a multiplication factor is needed, in the representation of the product of two CPS points, on the corresponding CPS plane. Our initial problem in understanding the reasons for the orientations of the CPS lines is now completely solved. The symmetries of the four related complex numbers, A, B, C, and D, are the same symmetry seen in the orientations of CPS lines. In conclusion, the CPS space is made up from an infinite number of discrete CPS planes. These planes can be associated with discrete complex planes. The Gaussian plane is just the simplest CPS plane. The concept of Gaussian primes, and other related concepts, can be extended to all of these planes. We will investigate these new prime sets at some point in a future video.